is RobertMains. Rob is a 40-year industry veteran and currently the general manager of ChipsAlliance, which is part of the Linux Foundation. Rob is a former engineering vice president of Oracle and distinguished engineer at Sun Microsystems, where he led an organization of over 200 software researchers and developers. Prior to that, Rob was a principal engineer at Magma Design Automation and originally a senior engineer at IBM, involved in numerous technical areas for the development of IBM Power and S390 systems. Rob has in-depth experience in software development, electronic design automation, IT management, semiconductor technology, microprocessor circuit design, and chip construction methodology. He is the holder of 13 US patents. The title of his presentation today is Accelerating Time to Market, Open and Collaborative Innovation in the Hardware Development Ecosystem. So, ladies and gentlemen, without further ado, please help me to welcome RobertMains.
Thank you so much, William. It's a pleasure to be here, and thank you for the honor to be able to present to folks today. So hopefully that shows my starting slide for everyone. So this is a new area for me in my career, which is in the arena of open source hardware development. And as my colleague Ted Spears just previously mentioned, we are seeing a rapid innovation in the overall hardware development ecosystem. It's really a change from what has been historically in the past, I think, as everyone knows. So I will talk a bit about that and then draw parallels to what we saw in the software ecosystem by comparison and how they have very much similarities between the two. So as William mentioned, I have about 40 years of industry, and if you can see here in my background here in my office, I have a chart that says keep calm and carry on. And that was my motto when I was in charge of design enablement at Oracle. And I think as everyone here knows, working on the latest semiconductors, it does require a degree of calmness, if you will, as well as humility, because we know that the stakes are high and the opportunities for failure are quite often. So both humility and calmness are two important parts. But that said, it's been very interesting career. Like Ted, I started in upstate New York with my education. I have a bachelor's in electrical engineering from Union College, actually, which is not too far from Cornell, and then a master's in computer science that I got courtesy of IBM and National Technology University. But I want to say this one thing, that over the years of observing this, that a change is the name of the game. Things are always evolving. There's always something new. And generally speaking, it's always improvements. So if we look at the history of computation, if you will, it's really more than just Moore's Law. Of course, Moore's Law has provided us with tremendous benefits in terms of allowing additional capability to be put onto a single chip with greater performance, less power, less area. So that has really enabled much innovation. But that's not only the aspect of it. There's also in terms of what's happened in packaging. If we go back in time with the multi-chip modules that first came out in the late 70s, early 80s, and continued to this day, to now the AIB or chiplet type of protocol that Intel originally was one of the innovators in, but then also has had quite a bit of contribution from AMD and others, and there is a new collaborative effort on that now. We just heard about domain-specific computing, and that's very much true. We're seeing that in my final years at Oracle. We developed a database acceleration unit that would specifically accelerate queries to the Oracle database. And of course, that was captured through the architectural analysis of calls that were made of commercial workloads to Oracle database and to see how we could actually accelerate that. So a key backplane to this entire picture here, which I don't really talk about in the chart, but is really the underlying computer architecture. That really is the inherent aspect of any of this work. And if the architecture is not right, it's not going to make a really much difference as to how good the process technology is, how good your time enclosures, et cetera. If the architecture isn't right, there's a fundamental problem that you would have to do. In any event, accelerators and domain-specific type of execution are becoming a real thing. And then also, as mentioned just recently, just now too, software. The compilers and the libraries are key aspects as well. I know when I was at Oracle, a key challenge that we had was that the Java runtime libraries were not optimized for Spark microprocessors, but were optimized for x86. So that was a real hindrance in terms of the performance of the Spark processor to the end customer. The chip itself was fine, but the libraries were a problem. So that was an item that had to be taken care of. But there's something new in the front here too that I want to chat about a little bit about. And that's really going beyond all the typical technical accelerators that we see. And what that's really is talking about how industry is changing. We're really going from a siloed type of model that we have historically seen in the past to more of collaboration. Now, with recent events in the world, as we see, it's hard to say exactly where this will shake out. But if we look back in the past, we can look at large companies like IBM as an example, or we can look in the automotive industry, such as Ford or General Motors, where everything was done in-house, from owning the rubber plantations to make tires, to owning the mines, to mill the steel or coal, to actually help build that into motors. Or in IBM's case, as an example, it's also true for the original AT&T, that it was all the way from process technology up through the design, through the software to build the entire product. Everything was there. And then we've migrated more to what I call supply chain management type of thing, or just-in-time delivery, where a given company will rely upon different partners in the industry, whether it be a foundry provider such as TSMC or Samsung or Global Foundries, or to some of the major EDA companies to provide the necessary services for your company to build its given product. To where we're now moving to what I call more of an open collaboration environment, where different companies are coming together along with universities and individuals to collaborate on different products and problems in a collaborative fashion. And what this really boils down to, aside from accelerating innovation, is also modulating the R&D spend and the NRE costs associated with building product. So it's a change in how we've been doing things in the hardware arena. But this is not necessarily a new idea. If we look at software, it has evolved quite a bit. So years back, there were punch cards way back in time. Code was written in an assembler. It was even written in Octal, right? When I first started my program in studies years back, I had a mini computer that I had to write code in using Octal, which was an interesting, right? Flowcharts, line printers, etc. More modern evolution, if you will, comparatively speaking, would be VI and Emacs or DBX and GDB. But now if we look at it, it's really a lot of fun to be a software developer, right? And that's in part, I think, the challenge we need to solve as from an engineering perspective for hardware engineering. But for software, right, everything's object-oriented. There's a lot of productivity tools. You can write it once, it runs anywhere. You have reusable components to pick from to build what you want to do. Tons of library available on demand, just magically goes out and finds things for you. And it just makes it, just a pleasurable experience. So what this is really all about is accelerating innovation, increasing productivity, and doing it with less resource, right? So it just makes life a lot simpler. You pick up components, they work, and it saves you a lot of development time on yourself. And so from a historical perspective, you also may recall that back in the early 90s, there were a lot of different operating systems, right? Some may recall VAX CMS from Digital Equipment, right? There was HP-UX. There, of course, is the mainframe operating systems from IBM, Z/OS. One of my alma maters, which was IBM actually, and also Sun Solaris was still around, very prevalent, OS2. And then something came on the horizon called Linux. Of course, Windows was out there at this time. And I recall the first time I heard about Linux when a colleague of mine showed up in my cube and said, hey, I've got this new thing I'm playing with called Linux. It's kind of like Unix, but it's a bit different. And it's like, yeah, whatever, sure, I suppose it'll evolve into something. Well, sure enough, it did. So that now is comprised of the Linux Foundation. That's more than just the operating system that all of us pretty much in engineering use to build chips. It has about 1,500 members, participation from 40 plus countries, all of the Fortune 100 telecommunication and tech companies, 30,000 some developers are contributing code. And it covers a wide range of things from security all the way down to motion pictures. So there's just a wide swath of areas that Linux Foundation is involved in. So then the question is what about hardware? Well, we heard a little bit about that in Ted's presentation. RISC-V International is part of Linux Foundation, as is Open Power. And ChipsAlliance kind of bridges both gaps. We cover different aspects of these things. I'll chat a little bit more about that. But hardware itself is seeing a huge, tremendous growth right now, right? In terms of 5G, advanced computing, healthcare, Internet of Things, et cetera. So by the year 2050, there should be over 100 billion types of different chips, which also is why we have a chip shortage in some regards too, right? There was pent up demand because of the pandemic, but the fact of the matter is, it's just so many things in our daily lives have chips. I recently had my garage door opener replaced, and the reason it was is because the chip in the motherboard in the opener blew, and the cheapest thing to do was just replace the whole thing. So lo and behold, that's what we did. But that's just an example of where your silicon is these days. So the open hardware growth has been tremendous, as Ted was mentioning, and ChipsAlliance is part of this with RISC-V, and you can see this, right? That, you know, the amount of participation in RISC-V has grown tremendously over the past 5 or 6 years, right? ChipsAlliance itself is a 3-year-old organization, has 37 members to date, and is active participation and growth. So we cover many different areas aside from a particular instruction set. We cover things such as implementation, open or source tooling, open source PDKs, verification suites, etc. And just to give you one more example of the growth interest in RISC-V, it's up to 62.4 billion cores are projected by 2025. And of course, Ted already mentioned about the investment that Intel has made in that, which is an important aspect. So ChipsAlliance really is fundamentally about building an open source design ecosystem, right? All the way from specification, RTL, process design kits, tooling, the actual physical implementations, and standards. And this would really allow us to create a broad open spectrum of innovation across that. Now, one of the things that you may ask is, well, why are open source PDKs such a big deal? Well, here's the thing. For those that are knowledgeable in building chips and dealing with semiconductor manufacturing companies, PDKs are an inherent part of the ingredients of what they do to actually build the chips. And typically speaking, you have to go through a long legal negotiation process and sign a non-disclosure agreement. But having open source PDKs and not requiring documentation, legal documentation to be signed relative to non-disclosures really opens up the ecosystem of innovation and allows for different companies and universities to come together and collaborate on a particular problem area. So it really simplifies and solves a problem. That doesn't mean to say that companies cannot come together on proprietary things as well, but it just has additional levels of challenge because of the legal underpinnings involved in doing that. Another key aspect of trying to help move innovation, of course, is enabling design, reuse, and interchange. That could be in the forms of soft IP, such as logical macros that are synthesized through electronic design automation tooling to a particular target technology the chip is in, to hard IP that could be commercially licensed or could be provided via open source that you can then just place in the particular chip technology they're trying to do. And then chiplets, as I mentioned earlier, is a newer concept of having small chips, as you see in the photo there on the right, that are comprised of different types of IP that you might pick up. And I have another chart on that a little bit further down the right. But the basic idea is that you can pick up IP in a catalog, whether it be open source or private, know that it's good, and use that to build silicon for your product. So let me just talk about a few examples from ChipsAlliance. So as I just had mentioned, the AIB interface, and here's a little bit more detail, but effectively AIB provides for an electrical protocol for different chips or chiplets to connect with each other, a standardized interface. And that takes a lot of the engineering and electrical work out of the problem set for a developer of another chip. So you can pick up a chiplet as an example from one of the menu on the right as an example, and then use that on a higher level package with your IP that you build, where you follow this protocol and then build the particular innovation that you're interested in. So it takes a lot of the challenging work relative to devising the actual underlying PHY layer and also the protocol as well. A project that we're trying to get going in ChipsAlliance, a collaboration project, is an open source DDR controller. And we are in talks right now to help start getting this project going and use it as a collaboration vehicle to help show or demonstrate the power of open source innovation. We'll likely start out in an open process technology node, a more mature node, but then move it towards a more advanced node, say in 12 nanometer, sometime in 2023. So this is something that we're trying to do to help demonstrate the power of open source and collaborative development. And as was mentioned earlier too, we've been working with RISC-V on a cache coherency protocol known as OmniExtend. And really what it does or allows for is to allow for a collaboration or cache coherent collaboration mechanism between different types of CPUs. RISC-V showing here, could also be a GPU or an FPGA, AI accelerator, et cetera. But the idea is, again, is to come up with a standardized protocol that different members can participate in. And that's being done as a collaborative effort with RISC-V. The RISC-V SwordCore ecosystem, the SwordCore was developed by Western Digital, and the overall verification suite, along with the Verilator open source verification functional simulator, has been provided to ChipsAlliance to allow developers to pick up this design and then use it with the IP that they want to build themselves. And along with that, the system Verilog and also the UVM based random test generator suite has also been provided as part of this for verification of that to the engineering community. Let me talk a little bit more about EDA. So one of the things that we're trying to do, and I think this really kind of dovetails into getting more people interested in hardware engineering. So for those that have gone through the engineering education, I've also experienced it professionally. Engineering is a hard field. I think there's no getting around it, or I'm not going to try to mince words on that. But I think there are things that we can do to make it more attractive. And a lot of this has to do with, aside from understanding the low-level details of transistors, as an example, which originally was a hand-tuned, hand-placed and routed type of thing, and understanding all the electrical effects below that. And then we migrated in time to gates, or our first level abstraction, and then into more of an RTL type of approach, which has been the most recent usage typically. And I would say that's a little bit more like writing an assembler. For those of us that have had that experience, writing an assembler is certainly a noble undertaking, but I cannot say it's necessarily fun. Similar to RTL, right? So a more fun approach is to write it in a higher language. It's more of a software approach, whether that be Python or some type of object-oriented based language that has offered with it libraries of services. It's easy to use or easy to reuse and has integrated verification associated with it. And then we have a set of tools that basically compile it and spit out, if you will, gates or transistors that can be used to help move that. So the overall idea here, aside from making it fun, is to accelerate innovation and increase productivity with less resource, similar to what we saw in the software arena. The other thing I want to say, and this is kind of an interesting thing, is what I would say is changing culture, which is overcoming the fear of failure. So for those that have been through chip tape outs, it's a multi-year endeavor. Usually it's very expensive to tape out a chip. There's a lot of engineering time and effort used to do that. So I make it kind of akin to, it's like launching a mission to Mars, or if you've seen Apollo 13, you know what I'm talking about when you see the folks in mission control waiting for the launch to happen, right? It's basically all systems go. And it's kind of a result was a paranoia, a fear of failure. So not to quote Andy Grove here, but maybe the paranoid only do survive, right? But that's really kind of the mentality that typically exists in engineering, right? And particularly for modern processes, right? Where it's, as I said, it's a multi-month effort and it's a multi-million-dollar undertaking. So, we're really trying to change that, right? Remove that failure is not an option type of paradigm to allow for more tape outs at low cost and older nodes. And that certainly is, what we've been seeing in the case with both what Skywater has offered and eFabus, is to be able to do that type of thing, right? And so this is kind of similar to what we've seen in commercial space launches like SpaceX Blue Origin, right? To make it more common and make it easy. The other aspect, of course, is to make hardware more like software, right? So that again comes into providing different language choices that folks can use, whether it be Python, System Verilog, System C, Chisel, which is an object-oriented language based upon Scala. It really improves the designer productivity and simplifies the overall thought process. It allows for libraries of functionality to be used to help build what you're trying to do. Encourages object-oriented thinking. And I believe this will help encourage broader participation by the community, not just your traditional hardware engineers, but also software engineers who are really interested in understanding how this all works. And then high-level synthesis to actually go then generate the RTL. And then you have implementation tools that will help to realize it into gates and transistors eventually in layout, and effectively rely upon those to provide guardrails to help guide you, if you will, to a safe landing for the chip that you're trying to design. I mentioned this earlier, but of course we have extensive effort or collaboration in the area of open source verification with UVM and Verilator, Verilator being an open source event-driven simulator that is used extensively for design verification. And another important aspect, of course, is to be able to prove and design more quickly. So as I mentioned in the earlier chart of providing guardrails, there is quite a bit of effort relative to being able to synthesize a design or to generate analog circuits with some type of generator. And there's a number of different tools, open source tools that are available to do that. Another key aspect, of course, is source verification and doing this in a rapid fashion. Being able to map a design onto an FPGA allows for much more extensive verification of that design before you actually tape it out and then receive the silicon back. So that allows for much quicker verification, less expensive verification as well. So specifically on digital implementation flows, the US government has funded a program called Open Road in conjunction with University of California, San Diego. And this is your traditional, if you will, digital implementation flow from logic synthesis all the way to layout, including timing and power analysis as part of that to ensure that the digital block does meet the objectives of what you're trying to do. There's also work in the analog area. So you'll see here the analog work group mentioned. ChipsAlliance has a number of different work groups involved that collaborate on different topics, from FPGA to design languages such as Chisel, for example, to analog to digital implementation. So we are working with a number of universities on different solutions in the analog design space. Automating analog is a challenging arena. This certainly will help also to broaden the ecosystem of participants in this world, because they don't necessarily have to know all the fine details required for analog design. We also have efforts in terms of the FPGA interchange format. So this idea here is an open source effort to provide a common interchange format for different FPGA suppliers and application developers to write to a common interchange format to allow for exchange of information of FPGA design in open source fashion. This was originally donated by Google and is now part of ChipsAlliance, and we're helping to move that forward. So to put this all together, I know I've covered a lot here. What we're really trying to do is to build an open design enablement ecosystem with a catalog of trusted ingredients. And that could be a trusted IP component library, could be an open source cell library, could be different macros, physical macros, and different types of tooling as well, as including also the verification test bench as you've seen on the left. So there's quite a bit here, and we have work to do to bring this all together, but we are making progress. And so what this is really all about, it's about building trust. It's more than just having an open source IP or application catalog, right? You need to have confidence to know that what you are getting from it is giving the right answer and it works, right? Software has built this in its community over many years with discipline. And one key difference between hardware and software is the fact that the confidence in the underlying design or technology can vary between the process nodes involved. So in other words, a circuit or a logic or physical block that may work at 20 may not work at 7, right? Because the underlying physical effects has changed. So your applications or your software applications used to design this has to update that accordingly. Relative to hardware IP, of course, you want tape out, productization confidence, you want to have a prevalence and availability of cheap shuttles available to help you prove these things in to make sure that they are work. And of course, for EDA applications, regression testing and quality results are key parts of the development process. And qualification of the foundry data is a key aspect as well, right? So does it correlate to the extraction? Does the timing correlate, et cetera? Are the DRC rules correct as well? So there needs to be further work in terms of building collaboration bridges between foundries and open source EDA applications. So to sum it up, what we're talking about is building an open source model of IP and innovation to help build your product. Really to have a trusted open IP catalog that would allow you to add your innovation on top of that to build a product that you are trying to take to market. And then putting this all together, it's really an open IP community and a business services type of model, right? Similar to what came about with the Linux operating system. Companies such as Red Hat were formed that help foster a developer community, and then have service companies such as Red Hat that could put this together into a product that is built and supported for end users to use. So in conclusion, open source hardware verification tooling are here. They're gaining momentum. It's growing quite rapidly, as we are seeing. Hardware engineering is learning from software. Abstraction, object-oriented design, libraries of functionality are things becoming a reality that help ease the burden of learning how to do this. And companies and universities are collaborating on mutual challenges of interest. And as I just mentioned, the business models are moving forward to help embrace this. And companies are innovating at higher levels, leveraging open source IP, accelerating time to market. ChipsAlliance, as part of the Linux Foundation, is a venue to provide a collaborative opportunity for all to participate. So with that, I will stop. Thank you.
Wow, thank you, Rob. That's leveraging 40 years of experience. That's thank you so much. That's and part of that is just a very nostalgic, right? You talk about punch card, OS2, mini computer. Reminds me my days in IBM Rochester, where we support the wire and network protocol microcode using a language called PL8, which I believe was developed in the East Coast, IBM out in New York somewhere. You probably know that better than I do.
Yes, I'm familiar with that.
So yeah, again, we welcome our audience to post the questions in the chat. But just real quick, especially you talk about making things easier, getting more people involved, right? In particular in the EDA space, it was very intriguing, like using Python for RTL, for example. So what do you think? When you talk about that, what's the reaction? And what's the impact on traditional EDA companies such as Synopsys and Cadence?
Well, I think when I talk about these things or mention these, people are excited about that. They're interested in different ways of thinking. But I will say it depends upon the audience that you talk to, right? So, there are, how shall I say, the crusty individuals who's like, that'll never work. But on the other hand, and crusty can apply to anyone. It doesn't mean any specifics, but there is a definite problem if you chat with professors at leading institutions. So I chat with professors at Berkeley, at Stanford, UT Austin, just to name a few, right? But there's a real challenge in getting students interested in learning about hardware or electrical engineering. And so I think by being able to describe designs in a higher level language, such as Python, which is kind of the popular language right now, that will greatly improve that. If you hand someone basically a Verilog manual as an example, their eyes are just going to glaze over. It would be akin to me handing you, a mainframe assembly programming language book, right? It's like, you got to be kidding me, right? So, I mean, not that there aren't needs for that, right? But there are better ways to do things, more productive ways and more fun ways. And then I think EDA companies are trying to address that. I mean, one of the members that we have in ChipsAlliance that's EDA company, Siemens specific, I'll mention it since it's public record, but they're very interested in what the open source community can do, right? And I think also in terms of how different design languages can be utilized or advanced to help improve productivity for folks.
Yep. Great. Yeah, hardware is hard. So Rob, please keep up the good work. We all need to find ways to get younger people involved, by kind of lower the bar just slightly a little bit. So keep up the good work.
Thank you.
Yeah, and thank you for your time. So yeah, we're going to see Rob again during the panel discussion.